right, thank you all for waiting. The next talk is going to be Under the Hood of Type Systems by Craig. So Craig is going to tell us a bit about fundamentals of how the type systems work. Off to Craig.
So hi everyone, my name is Craig. I struggled to find an explanation from a low-level view of exactly how a JavaScript type system compiler is implemented. I understood many of the jobs of the type system, but was really unsure on the mechanisms involved and how they work together. So this talk aims to shine a light on the fundamentals at work under the hood. It's not possible to focus on everything in one talk. So here we're going to be looking at type checks specifically. We're going to start with an overview of type systems, then build our own compiler which can run type checks and output some sensible messages. So first, a little bit about me. I'm producing an Under the Hood of series, which this is actually a part of. So far it includes Webpack, React hooks, source maps, VS Code, and there's a couple of others. They usually include building a small proof of concept to demonstrate the internal mechanisms of the tool. I'm an engineer at Fit, we're a startup helping people create fitness habits. I'm a member of the Mocha core team for a little over 2.5 years. So I'm a big advocate of testing and open source. I'm a big football fan of the championship club, QPR. And you can find me on Twitter and GitHub at CraigTop. So this talk is going to be broken down into two parts. Plan A, part A, is going to be an overview of type system compilers, including TypeScript. We're going to look at syntax versus semantics, what is AST, types of compilers, language compilers and their jobs. And then part B will be building our own type system compiler, which looks at the parser, the checker, running our own compiler, and then finally, what have we missed? And that's going to be having a look at what the things that ours do not do that most other compilers would do. So let's start with an overview. So something which is important to run over early is the difference between syntax and semantics. Syntax is typically code which is native to JavaScript. You're essentially asking if the given code is correct for the JavaScript runtime. For example, the below might be syntactically correct, although ignoring the type, and then the semantics. So this is code specific to the type system. That is essentially asking if the given types attached to the code are correct. For example, the above could be syntactically correct, but semantically wrong, as we're defining a variable as a number, but setting it as a string. So before we go much further, we need to take a quick look at one of the important mechanisms inside of any JavaScript compiler, that's AST. So AST stands for Abstract Syntax Tree. As I'm sure many of you are aware, it's basically a tree of nodes representing a program of code. A node being the smallest possible unit, and is basically a plain old JavaScript object with type and location properties. All nodes have those two properties, but based on the type, they can have various other properties as well. So in AST form, code is very easy to manipulate. So operations like adding to code, removing, or even replacing parts becomes much easier. An example is the code at the top, the image, and then just below that is the AST it would produce. And there are websites such as astexplorer.net, which are great at letting you write some JavaScript code and then immediately seeing it's AST. There are really two types of compilers which exist. There are native compilers, which convert code into a form that can be run by a server or a computer, i.e. machine code. A compiler such as the one found in the Java ecosystem converts code into bytecode and then into native machine code. And then there's a language compiler, which is quite a different role. The compilers for TypeScript and Flow and most other JavaScript tools both count in the category as language compilers, as they output code into JavaScript. The main difference with native compilers is that they compile for tooling's sake, so for optimizing code performance or for adding additional features, not to produce the machine code. They all still rely on the JavaScript runtime native compiler to do that. So a few of the core jobs found in any type system are: one, performing type checks. By this, I mean the introduction of types, often via explicit annotations or implicit inference, and a way to check that one type matches another. Then there's two, transforming code. Many type systems contain code which is not supported in native JavaScript. For example, type annotations are not supported, so they must transform from unsupported JavaScript to supported JavaScript. I actually explored transforming code more in my post on web bundlers and my post on source maps. And then three, run from a language server. So for a type system to work in a development environment, it's best if it can run any type checks in an IDE and provide instant feedback for the user. So language servers connect the type system to an IDE. They can run the compiler in the background and rerun when a user saves a file. Popular languages, such as TypeScript and Flow, both contain a language server. So for VS Code users, the main extension spawns a language server. You can actually see my blog post on VS Code for a bit more of an in-depth look at those. So as mentioned at the start, we're just going to be focusing on point 1 today. So that's performing type checks. So how does a language compiler work? So now we're going to look at a couple of the steps required to perform all the previously mentioned jobs in an efficient and scalable way. There are 3 common jobs to most compilers in some form of another. Step 1 is where you pass the source code into AST. This involves lexical analysis, which is turning a string of code into a stream of tokens, and then syntactic analysis, where we turn our stream of tokens into its AST representation. Parsers are responsible for checking the syntax of the given code. A type system will typically have to house its own parser, often containing thousands of lines of code. A lot of them are open source, like Babel and TypeScript, but actually a lot of the bigger libraries house their own. So the Babel parser is just over 2,000 lines of code to process the code statements, which can understand the syntactical analysis of any compiler-specific code, but also append the additional information for types. The Hegel compiler parser appends an additional type annotation property to code, which is a type annotation. And actually, we'll be looking a bit more at that shortly. TypeScript's parser, is a whopping 8,600 lines of code. It houses an entire superset of JavaScript, which requires the parser to understand all of it. So it's far larger than most that you find. Step 2 is where we transform the nodes on AST, where we manipulate the AST nodes. Here, any transformations to apply to the AST are performed. And then the final step is to generate source code. So here we're going to turn AST into a string of JavaScript source code. The type system has to map any non-JS compliant AST back to native JS. So how does a type system compiler fit into this? As well as the mentioned steps, type system compilers will usually include an additional step or 2 after parsing, which will include the type-specific work. So on a side note, TypeScript actually has a total of 5 phases in its compiler, and they are the language server preprocessor, which works via import, the parser, the binder, the checker, and the emitter. So as you can see, it's got a preprocessor which triggers the type compiler to only run over the files which have changed. This will follow any import statements to determine what else could have changed and would need to be included in the next rerun. Additionally, the TypeScript compiler actually has the ability to only reprocess the node tree branch of the AST graph, which has changed. That's actually a technique known as lazy compilation. So previously run AST can be stored in memory, which it calls look-aside tables, and then that allows for even faster compilation in the future. So for general type system compilers, there are 2 common jobs. There's inferring. So inferring is required for code which does not have an annotation. Using a predefined algorithm, the engine will calculate what type for a given variable, what the type for a given variable or function is. TypeScript uses the algorithm best common type, and it applies this inside of its binding phase, which is the first of 2 semantic parsers. It considers each candidate type and picks the type that is compatible with all other types. Contextual typing comes into play here, which is using the location in the inference. TypeScript actually introduces the idea of symbols. These are named declarations which connect declaration nodes in the AST to other declarations contributing to the same entity. They are the basic building block of the TypeScript semantic system. And actually, when I was digging through it, it was kind of relatively easy to get pretty lost with them. It's a huge system built with symbols. So I've tried to not follow that same approach so we can kind of really show the mechanisms here today. And then the second common job is checking. So now that inferring is complete and the types have been assigned, the engine can run its type checks. They check the semantics of the given code. And there are many flavors of these types of checks, ranging from mismatches to non-existing types. For TypeScript, this is the checker, which is actually the second semantic pass, and it's 20,000 lines of code long. So I really feel that that gives a strong idea of just how complicated and difficult it is to check so many different types across so many different scenarios. The type checker is not dependent on the calling code, i.e. if the file executes any of its own code at runtime, the type checker will process each line in a given file itself and run the appropriate checks. So that's it for part A. That's the overview finished. So now we're going to be looking at building our own compiler, which can run type checks for 3 different scenarios and throw a specific message for each. The reason we're going to limit it to 3 scenarios is so we can focus on the specific mechanisms that work around each one, and hopefully by the end have a really strong idea on how to introduce more complex type checks. We will be working with a function declaration and then a function expression, and the expression is going to be calling that declaration. So these are the scenarios. So scenario 1 is going to be an issue with a type matching a string versus a number. You can see we've defined a function there. We've got a type of number, but we're calling the function with a string. We've got scenario 2, where there's an issue with using an unknown type, which is not defined. So again, we're defining our function, but this time with a type which does not exist. And we're calling our function with a string again. And then scenario 3, where there's an issue with using a property name not found on the interface. So we've defined an interface, we've defined a function which should be using this interface, and now we're calling that function and actually handing it an object with the wrong property name. So those are our scenarios. Now onto the compiler. There are 2 parts to the compiler. There's the parser and the checker. And as previously mentioned, we won't be focusing on the parser today. We're just going to be following the Hegel parsing approach of assuming a type annotation object has been attached to all the annotated AST nodes. So what I've basically done is I've hard-coded the AST objects. So we're going to go through that now. So scenario 1 is going to use this parser and AST. So we've got to imagine that it's already been put through the Hegel parser. I've actually put a comment above any of the AST block to clarify what code it's for. So on the left, on line 3, you can see the expression AST block for our top line expression statement, which you can see actually on line 2 commented out. And on the right, on line 21, is the declaration AST. This is for where we have declared our function on line 20, commented out. So staying on the right, on line 46, we return a program AST object, which is the program with both AST nodes in. The program body is basically an array which is going to be holding these objects. So inside the declaration AST, on line 31, you can see the type annotation on the param identifier A, which you can see on line 30, which matches where it sits in the code. So this is what I mean by I've hard coded the actual Hegel, the parser's type annotations. On scenario 2, it's going to be using this parser, an AST. It's very similar to scenario 1 with its expression, its declaration, and program AST blocks. The code is seen on line 1. However, the difference is on line 12. The type annotation inside the declaration's params array is made up type. And you can see it on line 16, instead of what scenario has, which was a number type annotation. And we can actually see that if we go back and you look on line 30 slide, line 35 on the right, you can see the number type annotation. And so if I go back to scenario 2, you can see it's now made up type. So the expression and the program AST blocks are identical to scenario 1. So I haven't displayed them here again. So that's really the main change in scenario 2 between the 2 AST blocks. And then finally, we've got scenario 3, which is going to use this parser and AST. I apologize, there's a lot of code on the screen, but it's just to get across how the objects look going into the program. So as well as our expression and declaration and program AST blocks, there's now an interface AST block, and that's on the left. And you can see that the AST starting on line 4. And you can see the type, the interface declaration on line 5. Also, looking on the far right now, the declaration AST now has a generic type on its annotation. And you can see that on line 74. So instead of it being a string or a numeric, it's now a generic type. And that's actually just something I've called it because it's an object. And this is the part that takes our object identifier, which is person, and you can see its name on line 77. And the initial code for this is on the top, on line 60. So similarly to scenario 1 and 2, the program AST is going to return an array of these 3 objects for this scenario. So you can see on line 50, if I go back to scenario 1, the program AST body in scenario 3, it's going to be an array of all 3 AST blocks. Whereas for scenario 1 and 2, it's just got the expression and declaration. So as you can see from this previous slides, the main area which actually holds the type annotation object for all 3 scenarios is the declaration parameter, which is the declaration AST. All 3 have that in common. So you can see line 71 here, got type annotation, line 12 here, type annotation on scenario 2, and on scenario 1 on line 34. So, and all of the type annotations are under the declaration AST. So now onto the part of the compiler which does our type checks. We've got 3 slides to look at for this, all under the single function, which is called checker. So what does it need to do? It needs to iterate through all the program body AST objects, and depending on the node type, do the appropriate checks. We're going to add any errors onto an array to be returned to the caller for printing, so we can actually see the error. So before we go any further, the basic logic we will work with for each type is this. So for our function declaration, we're going to check the types for the argument are valid, then check each statement in the block body. For our expression, we're going to find the function declaration for the caller. We're going to grab the type of the declaration's argument, lastly grab the type of the expression's call argument, and then compare them to make sure that they're the same type. So this code contains the type checks utility object and an empty errors array, which will be used to check our expression and a basic annotation check. So nothing has been called yet, we're just defining this utility object. So this object has got, this is for the expression, there are 2 types of checks. So on line 13, you can see the numeric type annotation. Here, the caller type should be a numeric literal, as you can see on line 14. So if it was annotated as a number, the caller type should be a number. Scenario 1 would fail here, but nothing has actually been logged yet. There's also a generic type annotation on line 15. And if it's an object, we search the tree for an interface declaration, the scope. You can see on line 19, and then we check each property of the caller on that interface, which you can see on line 26 to 35. We're checking each property on the caller. And then if there are any issues, they're going to get pushed into the errors array. And you can see that on line 30 with a helpful message about what property name does exist and therefore what it could actually be. This is actually limited because it only works with the one object, but it's a proof of concept. Scenario 3 would fail here and get this error. So you can probably see that the processing is going to be limited to this file, to the file it's given. However, most type checks will have a notion of scope, so they're able to determine if a declaration was anywhere in the runtime and not just available in this program. Again, ours has an easier job because it's this proof of concept. So slide number 2, this code contains the processing of each node type in the program body. So this is where the type check logic that we defined previously is going to be called from. So let's walk through the code again and then break it down by type. So here we have the function declaration, which is where we would define our function. You can see that on line 48. So we start by processing the arguments and the params on line 49. If it finds a type annotation, which here it does on line 51, well, on line 51, check if the type exists for the argument given, i.e. the arg type. If it does not, add an error to the errors, which is on line 56. Scenario 2 would get an error here because the type does not exist. Lastly, we process the function body. However, as we know there's no function body to process, I've left it blank. The function body is the actual block of the function. And if you remember, when I defined the function, there was nothing actually inside of it. It was all about the arguments and the type definition. So now onto the last slide of code. This is the final bit. Here we have the expression statement at line 69 on the left top. First, we check the program body for the declaration of the function on line 71. So we've got to go off and find the declaration. This is where scope would apply to real type checker. So if no declaration is found, add an error to the errors array, which we're doing on line 79. Next, on the right, we check each defined argument type against the caller argument type. And then if there's a type mismatch found, then add an error onto the errors array, which we're doing on line 105. So both scenario 1 and scenario 2 will get this error. So what a mouthful. Now we can have a look at what this is outputted. So I've introduced a basic repository with a simple index file and some tests, which processes these AST nodes and logs the errors. When I run it, I get this output. So here you can see the errors for scenario 1 is type Craig string is incompatible with number. And I've actually just realized that that should probably be the string literal because it's the type that it should give us, but proof of concept. Then errors for scenario 2, we can see we've got the type Craig string, oh, I've done it again, is incompatible with undefined. So this would again be a string literal. And then we've also got type made up for argument A does not exist. This is where the type does not exist. And then errors for scenario 3, this is the interface. Property nam does not exist on interface person. Did you mean name? So if we are to summarize what these are actually talking about, scenario 1, we defined an argument type of number, but we called it with a string. Scenario 2, we defined a type on the function argument, which does not exist, and then we called our function. So we get 2 errors, one for the bad type defined, one for the type mismatch. And then scenario 3, we defined an interface, but used a property called nam, which was not on the object. We asked if we meant to use name instead. So that's it. It's a basic type checker in less than 100 lines of code. So what have we missed? As mentioned, there are many additional parts to a type compiler, which we've omitted from our compiler. And some of these are listed here. So we can start with the most basic, which is the parser. We manually wrote these AST blocks. Within a real compiler, these would have to be generated. Then there's the pre-processing and the language server. A real compiler has this language server mechanism to plug into an IDE and rerun at appropriate times. Ours doesn't. There's the lazy compilation. We've got no intelligence around what's being changed or storing any of the AST blocks in memory. The transform step, we've completely skipped the final part of the compiler, which is where it would be converted back into our JavaScript code, which can actually be read by the JavaScript runtime. And also scope, which is something we touched on a few times. As it's a proof of concept, it's all in a single file, didn't really need to know the notion of scope. However, real compilers have to be really aware of what has access to what. So that's it. Thank you so much for listening. I learned a huge amount from this research on type systems. I hope it was useful for you. You can find the repository for the code and the tests on GitHub at this link. And also you can check my site for more under the hoods, which is craigtaub.dev. So thank you very much for listening.
Right, I apologize for that. So once again, Craig, I'm gonna say good things about you multiple times. What's bad about that? Thank you very much for that great presentation. I think that was really insightful, especially that I imagine like a bunch of us just were aware of type systems, but like never actually even thought about how that thing works under the hood. So I have like a quick question for you. How did you come up with the whole idea of Under the Hood series? And how long have you been doing it?
So I came up with the idea about a year ago, and it was with Webpack, and it was all around module bundlers, and it was all about how does it, like I would look at the output from Webpack, see all my module code in an array, and think, how does my ES6 module become an object in an array, and when you look at the Webpack, the output, you can see the require calls. They require index 0, index 1, index 2, and I got thinking about how does it do that? And actually, it turns out it's not particularly complicated how it does that. And that got me thinking more about, well, actually, if it's possible to understand how Webpack works, maybe it's possible how TypeScript works, and how run systems work, and how React hooks work. And it kind of just took me on any time and I'm currently looking at GraphQL as well, and a lot of them share similar mechanics. And I've kind of found that once you understand the core mechanics involved, a lot of which are with AST, you kind of can really, it kind of helps you to understand how how to extend the tools that exist and how you could actually improve them. And so, and it's kind of a bit of a mix between a beginner's talk and an advanced talk. At the same time, I felt like it was explaining from a very beginner's level how things work, but also can help fill in the gaps on an advanced level. So, yeah.
Yeah, so one thing went through my mind, like while listening to your talk, and especially like after you went through your last slide. So in our unis, the courses that we've been through, like we were always taught about abstraction. And I think that what you did here, like, is absolutely perfect example of abstraction. Like, you completely ignored like loads of things that were that are really important, but you actually managed to explain to us like how part of that whole type system works. And I think that is just amazing. So how did you end up choosing like to do parsers as your under the hood series, or actually type systems?
Do you mean how did I pick the checker, or or type systems in general?
Actually, like, both of those are good questions. Thank you for your help.
So I guess, yeah, when I start doing the research just for myself, parsers are such a big, and a good example was the symbols. So my initial plan was to do all about TypeScript symbols, because a lot of the TypeScript documentation talks about symbols. And I thought maybe I can simplify this. But after many hours of research, it turns out there's a fair amount of things that you just can't really simplify to some degrees. And certainly not myself. Hopefully others can, and actually maybe produce some content that can help me to understand those. Yeah. And then the second part to that question, I guess the type systems, is just because they're such a fundamental part of what we do in the JavaScript ecosystem. On top of web bundlers, especially in recent years, we've gone from TypeScript and Flow being something that only would be used in the edge case to being something which is now completely ubiquitous as a convention. So it seemed like a critical thing to understand and to actually have an awareness on the mechanics involved.
All right, I think that's a pretty good explanation. And would you say that you learned quite a lot, like writing this? Actually, not specifically for just this specific project, but like throughout whole the Under the Hood series. I imagine that it's a really good way to help you understand, as you mentioned already, like Webpack, type systems. Would you say that those are the things that actually help you as a developer, like improve? Or yeah, that's it.
Yeah, absolutely. I've kind of, I'm in, I would say, a category of people who are very visual learners, who learn a lot by visually being able to comprehend the moving parts. And actually, something that I've learned through this process is, if ever I'm using a library, no matter what it is, it's within the JavaScript ecosystem, I always will try and put aside some time to go and look through the code and actually try and build like a small proof of concept to prove how it works. Even if it's just a session with some of my colleagues at lunchtime, just let's spend 20 minutes. Can we build a really small version of how this works? And actually, there's been a few that we've really struggled with. And actually, the React hooks talk that I've done, blog post that I've done, it came from one of those lunch sessions that I did with my colleagues. Yeah. I would say, and I wouldn't recommend people just my content is actually what I have learned from it, but actually there are vast amounts to be learned by going through it yourself, by spending the time going through it, because a lot of the time we can be siloed by how our own companies write code and our own design concepts. And actually the best way to really get some outside external help in it in a very quick space of time, unless you plan on moving jobs every 6 months for 10 years, and then you've seen 20 companies worth of design concepts. And even then, many will probably be long too old to be using anymore. The best way really to keep yourself up to date and understand what's really a good design approach in the JavaScript ecosystem these days is to just go looking through the tools that you're using, go looking through some libraries and CLIs and some of the frameworks, and just how do they actually work and how do they look? And you'd be really surprised. I have always been very surprised how much I come away with. So I would recommend everyone does spend a bit of time doing that, because you learn a huge amount.
All right. Thank you very much, Craig. I'd really love to continue chatting to you about this. It was really helpful, but we have to move on with our meetup. And yeah, thank you very much. We are handing off to Gleb, that is going to talk about Algolia search engine.